Thank you very much for inviting me and the introduction. So I talk about this Stringor bundle that we construct in joint work with Peter Christel and Matthias Ludewig. So you might know about the Stringor bundle. This is this classical thing one looks up to in differential geometry and particle physics. And the Stringor bundle is defined on a spin manifold. So how is a Stringor bundle defined? A spin manifold means that the tangent bundle, or the structure group of the tangent bundle, is lifted to the spin group. So one has a principal bundle for this bigger group, the spin group, and then one uses a representation of this spin group in order to form the associated vector bundle. So let me write this. So this is an associated using a representation of the spin group. So what is the Stringor bundle good for? For example, there are many applications of that. For example, one can, for physicists, most important, define what spinor fields are. Spinors on a manifold, sections in the Stringor bundle, and one can construct a differential operator, the Dirac operator. Which is used to write down the fermionic action functional. And so this operator is, of course, very interesting, and there is lots of theory involved. For example, there's index theory of these operators. And then one can look at the indices and wonder what they are. And if one has families of operators, the indices will not be numbers, but elements in cohomology series. And here, in this case of the Dirac operator, the relevant cohomology theory is K-theory. So this is related to K-theory. There are plenty of more things one can wonder. For example, what are the obstructions to form this Stringor bundle? The obstructions are only that the manifold is a spin manifold. These obstructions can be formulated easily by saying that the Stiefel-Whitney classes of the manifold vanish. So this is topology. And there are many more things. For example, one can look at the Stringor bundle from the point of view of anomaly cancellation. So fermionic theories have this fermionic anomaly, can be represented by line bundles on the loop space, and then the Stringor bundle sort of cancels this anomaly in a sense. Okay, so that's my motivation to go over to the Stringor bundle. So the Stringor bundle is this fantastic name, comes from the work of Stolz and Teichner, who have this programmed, among other things, to categorify this for strings, to string theory. So what the spinors are for point particles, we're wondering now what is the mathematical structure responsible for strings, string fields, string Dirac operators, and so on. And some of the things are known, most of things are not known. So this work of Stolz-Teichner is unpublished and 17 years old now, where they speculate about the existence of the Stringor bundle. So if we sort of correct this, so Stringor bundle is defined on a string manifold. So what's a string manifold? A string manifold is one where these characteristic classes vanish, and in addition, a further class, sort of this famous fractional first Pontryagin class, also vanish. So string manifolds are in particular spin manifolds, but with another cohomological condition on them. It's so that this Pontryagin class is defined for just oriented manifolds, like all the Pontryagin classes. So this is P1, and if you have a spin manifold, so a particular oriented manifold, then you can divide this class by 2. It's divisible by 2, right? It's integral cohomology. So you cannot just divide everything by 2, but for a spin manifold, you can divide this class by 2. And it's sort of more basic. You can divide by 2, you cannot divide any further, so that's the basic thing. It's 1/2 of the class, not the class itself. Okay. And what I want to talk about is that we now have a sort of a rigorous construction of this anticipated Stringor bundle, and it works just like here. So it's an associated two-vector bundle using a representation of the string group. Okay, and that's the main part of the talk will be to explain what the string group is and how the representation works, and then other things are sort of not known, but there are sort of famous and interesting speculations. For example, the corresponding Dirac operator will have something to do with Witten's Dirac operator on loop space that appeared in Witten's work from the late 80s. And this cohomology theory will not be K-theory, it will be another cohomology theory. So Witten computed sort of the index of this operator on loop space, which is sort of everything is ill-defined because he applies like all the theorems to infinite dimensional manifolds, which is not allowed. But the sort of the interesting thing is that the result that Witten gets in the end, that's well-defined. It's just a power series in the Pontryagin classes of the manifold, and Donzaguet has proved that this power series is a modular form. So it has something to do with modular forms, which is sort of amazing. And the cohomology theory relevant for this is this cohomology theory called TMF, topological modular forms. But that's just a conjecture right now. All right. So let me start doing some concrete things. So I wanted to talk about the string group. So the motivation for this group, also coming from this sort of vanishing of further obstruction classes, is to look at this sequence, which is already relevant for spin geometry. So, right, here are the manifolds, oriented manifolds, spin manifolds. So the structure group reduces or lifts to this group. And the idea of the string group is that it's one further step in this tower, and some people have already looked at the higher steps. So the point of this sequence is that this orthogonal group, it has some homotopy groups. For example, in 0th degree, it's not connected, and each step to the left kills the lowest homotopy group. So this group is not connected, it has pi 0. This group is connected, so it has no pi 0 anymore, but it's not simply connected, it has a pi 1. This group is connected and simply connected, but it has a pi 3. And the string group is 3 connected. So the next homotopy group would be in degree 7, but never mind. So we kill the homotopy groups from below. That's the meaning of this sequence. And so now, of course, the question is, now what is this group? You know that probably that the spin group has sort of various famous sort of constructions that how to construct this group. And people have tried to do this here, but it's sort of more or less easy to show that the string group cannot be a finite dimensional Lie group. It's impossible. It cannot have this homotopy type. And so the first construction of the string group was by Stefan Stolz in '96, who constructed it as a topological group that worked. And then there was another famous work on this by Baez, Schreiber, Stevenson, and Kranz, who proposed to view this group string D as a categorified group, a 2 group, and then gave a construction in that setting. So I want to recall that construction under a slight modification that I worked out together with Matthias Ludewig that sort of drastically simplified the original construction. So I want to talk about 2 groups. 2 groups. So what is this? So there are sort of many ways how to think about 2 groups. So for example, one can look at monoidal categories and where all the objects are invertible with respect to the tensor product. One can look at categories internal to the category of groups. So like categories which have a group of objects and a group of morphisms, and all the structure maps are group homomorphisms. So the simplest way to think about them, under some slight strictness assumption, is to think about them as crossed modules. So cross modules are a model for strict two groups, and it's very easy. So let me explain what a cross module is. That's an idea actually of Whitehead from the 40s, so it's very old. It's not any of these new fancy things, it's very old. So a cross module consists of two groups, so they're always called H and G, and there is a group homomorphism T from one to the other, and then this group has to act on H by group homomorphisms. That's the whole structure, that's it. And there are just two conditions on this. The first condition is that if I act, so G acts on H, so then I am in H and I apply T. So this is supposed to be equal to the conjugation action of G on T of H. Okay, so very simple equation. And then there is one other equation telling me what happens if I act with a G that is in the image of T. So if I act with T of H on an element H prime, then this is supposed to be simply the conjugation action of H on itself. So that's it. That's a cross module, and that's a nice model for two groups. In particular, it's nice because it is easy to internalize into different contexts. For example, now if I want to take topological two groups, then I just require that H and G are topological groups, T is continuous, the action is continuous, that's it. If I want to talk about Lie cross modules, then I require things to be smooth, and this string group construction of bias results in Fréchet crossed modules, and that's also what I will describe in a second. Just before, let me give some examples, some easy examples of cross modules. So one can try to see what the easiest examples are. For example, I can first try to put G, the trivial group. So I just take some group H, mapping to the trivial group. Then the trivial group can only act trivially on H, so there is no information. This is no information. So the only information is that the group H itself. And now we look at, this identity is trivial because it takes values in G. This identity is not trivial, by the way, that's this Pfeiffer identity, which is sort of very famous because everybody puts another F here, in particular the Germans, but it's wrong. The guy was called Pfeiffer, not Pfeiffer. And so this identity is non-trivial, and obviously this vanishes. It tells you that the group H has to be abelian. Okay, so this only works for abelian groups. Sometimes this crossed module is called BH. The reason is that there is a way to sort of take a geometric realization to an ordinary group, and then this is a model for the classifying space of H. So the other extreme is put H trivial, G some group, then G can only act trivially on the point. So again, there is just one group involved here, and there are just no conditions on this. So this is sometimes called G dis because it is, in this category sense, it has only identity morphisms. So this is the way how, so these two groups plays a role of groups in higher gauge theory. And this is the way how ordinary gauge theory, just concerned with a group, embeds into this higher context by making this construction. Okay, so there are more examples. For example, there is a group responsible for T-duality. So I do not want to talk about this today. So there is another group. And one example that's going to be relevant later is the following. Take an algebra, A. So can people see this, or should I move? Okay, I'll switch to the other blackboard in a second. So A is an algebra. Then we have the following crossed module. We can take the units of the algebra, and they map to the automorphisms of the algebra by associating to any unit the inner automorphism that is conjugation by this unit. And of course, the automorphisms act on A by evaluation. And it's a homework to see that, to show that the back two axioms are satisfied. So every algebra makes another crossed module. All right. A is not a group, but the units in A form a group.
But shouldn't it be there H on both?
Not sure what you mean. The group H is the group of units in the algebra. On the group of units. Thank you. Right, excellent. So it always acts on H, exactly, on the group of units. And of course, if you apply an automorphism to a unit, the result is again a unit in the algebra. So this is like, so first year algebra exercise, everything here. So that's sort of nice. Okay, so now let me come to the important example, namely the string group. So it's example number 5. So, and I really want to emphasize that the construction I give you now is complete and very easy, like very different as the original construction, which takes like 40-page paper because, okay, I'll tell you what the trick is. So there is one ingredient we need in the construction of string D. So first of all, we can make it more general. So first of all, let G any Lie group, okay, let's make it. So G, I just write G for the spin group. So we base the construction of the string group on the spin group. So G is the spin group. And what we need as an input for this construction is, so we go to the loop group, omega G, the group of smooth loops, right? Yes. Yes, so based loops. Based loops, yes. Doesn't matter in the end because we always restrict to identity things. So, and what we need is this basic central extension. So this is like a classical thing in this loop group theory, that the loop group of a simply connected simple Lie group has this basic central extension. Don't worry about the basic. There is a central extension that one can sort of construct.
You're now that there's a cyclic group of central extensions, and you're taking you're choosing.
Yes. It's a generator in the group of central extensions, which is Z.
Because that's usually presented as a central extension for the full loop.
Yes.
Now you're restricting it.
Exactly. Yes, that's true, exactly. So this is a classical theory, like for example in this book of Presley-Siegel, but also earlier it appeared. And so the trick that, so Bayes and the people use this, and the trick that sort of completely simplifies the story is it's a very stupid thing. We restrict to loops that have only support on the first half of the circle. So we call this omega 0 pi G. So if this is a loop, so here is the identity element, E, then this loop can only do something on the first half, and then is the identity on the other half, okay? So we can sort of just restrict, and then also restrict the central extension to this subgroup. It's a subgroup, of course. So we get another central extension by U1, and we use that central extension. So it's very stupid, but it helps. So why does it help? So here we have a map to the paths starting at the identity element in G, namely by simply restricting to the first half where the thing is non-trivial. So it's something like gamma goes to gamma, restricts to 0 pi. It's of course the loop again, because the thing has to end at the identity point again, but I ignore this and send it to regard it as a path, as a closed path. And then this map here, that's gonna be my map T from this crossed module. Okay, let's see. So my crossed module will consist of this group, that's H, that's G. This is my map T. Okay, it remains to construct this action of paths on this thing, and that's what was very complicated in in the first constructions. Here it's totally easy, I tell. So if I take a path, beta, and I want to act on an element phi here, so beta acts on phi, so we do the following. The first thing is, take this path and we double it to a loop. So if I have a path, it starts at the identity element and it goes somewhere, I consider the loop that does the same on the way back, sort of. It's like this. This is gamma, again gamma, and we get a loop. Eventually I will use the notation gamma cap gamma to say what happens if you have two paths and make that end at the same point, and you make it a loop by first running the first path and then running the second path backwards. Okay? Yeah, yeah. So in general, there is a construction like this. Take two paths that end at the same point and make a loop by going here and then the other backwards. It's what? That's a good question. That's a good question. There are some, so this belongs to the technical difficulties. So here I mean the paths, all whose derivatives at the endpoints vanish. And then it's smooth again. That's possible, but that's not a Frechet manifold. I want to remain in the category of Frechet manifolds, and unless you specify. Let's not discuss this here. Actually, I was happy with. I was. Okay, these are choices. Okay, but Frechet manifolds, it's like the easiest thing here to do, and that works. Okay, so let me explain this action. Okay, so we take this path beta. It's now our path. We double it, beta cap beta. Then it's a loop, and here. No, sorry, here, it's a loop here. And we have the central extension, it's surjective, so I can choose a lift. I make a twiddle over it, so I have chosen a lift in the central extension. And now I conjugate simply by this, that's it. That's the formula. And now one can check the two identities. The pi-phi identity is not satisfied automatically. Maybe that was a point that had not been realized before. The pi-phi identity requires an additional property of this basic central extension that's not in the classical theory. It's a property that we call it that it is disjoint commutative. It means if one has loops, two loops, and they are supported only on disjoint intervals, and then you have lifts elements sitting over these loops in the central extensions, then they commute. I mean, the loops commute when they are supported on disjoint intervals because the product is pointwise, but the elements in the central extensions do not automatically commute, but they do commute if the group G is simple and simply connected. That's a theorem we prove in our work that this is the case, so it applies here. And let's see, sort of the exactly, the conjugation doesn't depend on the lift because we have the central extension, so two lifts differ by U1 and drop out in the conjugation. Very good. So maybe I do this sort of little calculation how this disjoint commutativity is used. Okay, to prove the pi-phi identity. So now we want to prove this. So maybe I'll do it here. So want to prove this pi-phi identity. So I have to do a calculation like this, T of psi x on phi in the terminology there. And psi and phi are both here. Okay, so for simplicity, let's call this beta. This is a path. Okay, and then I write down what I just defined. This, and then again, a very dirty trick. I smuggle the psi here into this equation. Psi to the minus 1, psi to the minus 1, psi. Okay, this way. And so, of course, I can move this under the inversion, put it here. So now it's conjugation by this element here. Sorry, like this. Okay, so it's now conjugation by this element. And now, like a very simple calculation, using the stupid restriction to the first interval shows that this is a thing supported on the first interval, and this element is a thing supported on the second half of the circle. And by disjoint commutativity, these elements commute. The second true? Okay, so because psi projects to, okay, so here, so psi is an element in the central extension that projects, so T of this is beta, so this means it projects to beta cup and the constant path at the identity. This is the fact that it's only supported on one half, and that half is beta, okay? And this element beta cup beta twiddle projects to beta cup beta. Now we take -1, so inversion is pointwise, and if we multiply these two things, on the first half we get cancellation. So this is constant cup beta. So it's only supported on the second half of the interval. And that's it. That's the full construction of the string 2 group. Any more questions? Yeah. The space of objects is this path group, yes. Exactly. Right. Yeah. So in this general cross-module picture, what you just defined is, it's called the pi1 of the cross-module, is the kernel of the map T. It's in fact always an abelian group. And here the kernel of the map T is just U1. Right, because you want those elements in the central extension that are over the trivial loop, so you are in the kernel of U1. There is also pi0, by the way. Pi0 of such crossed module is G divided by the image of this map. And in this case, it's the path group divided by all paths that arise this way, that come, and the point is that everything in the image of T is a closed path. So you get something like all paths divided by the closed path. That's the same as just the endpoints of the path. So we get G. Okay. All right. What? Okay, so this is a quotient of the based path in G by the image of, well, the central extension, basically.
Because those paths are completely parameterized by what happens from 0 to pi, whereas the path space is parameterized by what happens from 0 to 2 pi. So it seems to me it's still an information.
Well, the paths, okay, so this is a matter of where the paths are defined. So here the paths are also going from 0 to pi. All the paths are going from 0 to pi.
But then how did you conjugate? Because basic goes from 0 to 2 pi. So I don't see how a path parameterized from 0 to 2 pi can act on a path parameterized from 0 to pi.
Because of this cup, it's two paths, each parameterized from 0 to pi. Yeah. So the cup is... The cup is just saying, take the paths gamma 1 and then compose path concatenation with the inverse of gamma 2 and reparameterize. Yes. No, this is parameterized from 0 to 2 pi. It's from...
How does a path that's parameterized from 0 to 2 act on a path that's parameterized from 0 to 1? This is what I
What do you mean by act? This is multiplication.
Multiplication at what parameter?
These are they're both elements of this group. It's
Yes, but you're saying phi is required to be the identity
look,
from pi to 2 pi?
look, phi is an element here, which is a subgroup of this. So phi is an element in this group, okay? Capital Phi is an element in this group, okay?
No, I mean, I think the question has been answered. P is paths from parameterized by 0 to 2 pi, which are the identity from pi to 2 pi.
That doesn't matter. That's like all the same. No.
Otherwise you can't write
So
that
then
formula.
do you mean this formula? Okay, then let me say again. So phi, capital Phi, was by definition an element here, so it's an element here in this group. Phi is an element in this group. That's how I assumed it. Okay? So beta cap beta is a loop in G. Okay, and then beta cap beta tilde is a lift to here. So beta cap beta tilde is also an element here, and then I can multiply.
No, because phi wasn't in the loop group. Yeah, phi is in the loop group. How is it?
I don't understand your question. I just explained to you that all the elements here are elements in this group.
How is something in the path space of G in the loop group?
It's not.
Oh, phi is in omega G. Where's that written?
Here.
Well, but
Here. Phi is in
beta is in P. Yeah, there.
Yeah.
Okay.
Better? Okay. Can I go on? Yeah. Okay. Yes, Miguel. Yeah.
So the spin group or G have a two-shifted symmetric structure. And now the string is kind of a quantum-like bundle for that. And it looks to me that the string that you are picking is kind of polarized. Do you thought of that? Or?
I don't know. You are the expert for this. Don't ask me.
Because you are just thinking how to fit it. So it's kind of a natural conversation.
So here this half is just like a trick to make this conjugation action, to enable this very simple definition of the conjugation action. So in the construction of bias, they are not taking half of it, and they have an utterly complicated definition of this conjugation action by going to the Lie algebra, writing down a formula, and integrating up and such things. But we don't need that. Okay. All right. So next I wanted to explain what a string manifold is. So maybe I have to cut this a bit short. So string manifolds. So the point is that there is a theorem, also due to bias, but also there are precursors of this by McLaughlin, and also Stefan Stolz had a version of that theorem saying that a manifold is a string manifold, so that just means that this 1/2 Pontryagin class vanishes, if and only if it allows a string structure in the sense that the frame bundle, now we come back to this geometric version, that the frame bundle, the structure group of the frame bundle, lifts to the string group. Okay? So, frame bundle lifts to string. So now string is one of these two groups, these cross modules. So what does that mean? So this means that what has to go into a higher categorical context, for example, one can use non-abelian gerbs, like Paolo defined it 20 years ago. So that's, how does it look like? So in these bundle gerbs, there is a point that you take the manifold you're working on, then there is a kind of resolution, surjective submersion. So it's here in this context, it's sort of good to choose the path space, like paths, so start at some fixed point x, but with a loose end. That's a surjective, the endpoint projection is a surjective submersion. And then one looks at the simplicial resolution with fiber products of this. And then a bundle gerb has something here on the double intersections, namely a principal bundle, P. And that's in this cross-module picture, it's easy to explain if I want to look at a sort of higher categorical principal bundle version, and if I have a cross-module, then the structure group will be H. So in the case of the string group, H is this restricted central extension, and the bundles are additionally equipped with an anchor with values in the group G, which is, in our case here, the path group. And here, so I have to sort of cut a bit, but here is sort of compatibility conditions. So that's how a bundle gerb works. You choose a resolution, and you have a principal bundle on double intersections, and you make it sort of compatible with the simplicial structure. And you can think about a lift of the frame bundle to the string group D as such kind of thing, a bundle gerb for the string 2 group. Okay, that's how I think about string structures. And now let me come back to this idea I started with, that we want to associate, so I wanted to generalize this construction that the spinor bundle is associated to a spin structure. Now I want to explain how the Stringor bundle is associated to a string structure, namely such a string gerb on the manifold. Yes? String D, as a 2 group, it was constructed in this work by John Byers and his collaborators. As a normal group by Stefan Stolz, yes. It's always that when you have these 2 groups, you can go to this geometric realization of that, and then it's up to homotopy equivalence, the ordinary topological group. More is not known. I mean, these models come from very sort of different aspects, and they are modeled like very differently, and there is no like isomorphism or so. I mean, the string group itself is only well defined up to homotopy equivalence, because in the sequence I explained that the point was vanishing of homotopy groups, so only the homotopy group of the group is defined by this. So the models can look very different. Yes, one can prove that there is no finite dimensional cross module for this group, yes. All right.
Here, this P is just a principal bundle, so there is no connection.
Yeah, right now there is no connection, yes. Connection is like, comes next year. Next talk. Yeah. Say again, this model is not? Yeah. Yes. So this model is strictly isomorphic to the Byers model. Sort of, it includes into it. It includes, yes. Chaumat-Priest model, I don't know. I mean, that Chaumat-Priest does not have a model, right? He proves that there exists a model up to unique equivalence. So yes, you can take this, for example, yes. So let me continue. So now the main part of the talk. So what we need for this associated bundle construction is now a representation of the string group. So that's the point. So a representation of string D. So let me sort of emphasize that finding a representation of any of these string group models was an open problem for a really long time. People have tried, and sort of we kind of managed it. There are sort of plenty of choices and conventions and things involved. So sort of we've been able to pick the right things. One thing that one has to choose when talking about representations of these higher categorical groups is on what are they represented? Right? What is the model for 2 vector spaces that we use? And we use the model where 2 vector spaces are algebras. And here, I mean, it's a bicategory of algebras. where the morphisms are bimodules, and the two morphisms are intertwiners. So that's a good choice with a lot of geometric intuition in it. And so, for example, note that two objects, two algebras are isomorphic in this bicategory exactly when they are Morita equivalent. So we sort of comprise sort of this sort of important algebraic notion here immediately. That's our choice. I mean, you can choose what you want. So, yeah, it's our definition. So classically, you would say like a bicategory qualifies to be a bicategory of two vector spaces if it's symmetric monoidal and the endomorphisms of the unit object is the category of vector spaces. Something like this. This is satisfied here. The unit object is the algebra K, the ground field, or C, and the bimodules of CC bimodules are just vector spaces. So that qualifies it as bicategory of two vector spaces. So now if we want to make a representation on a two vector space, we need to know what the automorphism group of an algebra is in this bicategory. And I mean, it's a bicategory, so every object A has an automorphism group in this two group in this bicategory. So let me use capital letters, right? It's an object and there are morphisms and two morphisms and they sort of assemble into a two group, a group object in categories. And so what is it here? So it's just the invertible AA bimodules, right? So it's like the A bimodules and they're the invertible objects. That's a nice Picard category. And unfortunately, there is a problem with that because we want to associate a vector bundle or two vector bundle. And if you associate along a representation, the representation has to be continuous at least, because otherwise the associated bundle will not have continuous transition functions. So we need to incorporate a continuity condition, and this here is just a discrete thing. There is like no manifold structure on the set of all bimodules, something like this. And so we choose a smaller model, namely exactly this example 4, this automorphism group A goes to out A, which has like a map to here, because on the level of objects, if I have an automorphism, I make a bimodule out of it by twisting one of the actions with the given automorphism. That's the main point. Now, sorry? So if I have an automorphism here, say phi of A, then I associate A phi. So where A acts by multiplication from the left, and the action from the right is first by using the automorphism and then multiply from the right. So this is an invertible bimodule. If phi is an automorphism, that bimodule is invertible. Of course, in general, we won't get all the invertible bimodules by this construction. There is a condition. Condition is called Picard surjective. An algebra is called Picard surjective if this map is surjective. Not every algebra is Picard surjective. However, every algebra over the complex numbers is Morita equivalent to a Picard surjective one. And this means that like letting our representations end here in this cross module and not in this is sort of no restriction at all in the end. And this is, if A is finite dimensional, for example, it's a Lie crossed module, right? The group of units in a finite dimensional algebra is a Lie group. The automorphisms are a Lie group, and it's a smooth cross module. So now we can talk about smooth representations. Okay, so this is a representation of some crossed module is a map to this, so to this automorphism group of A. Smooth, continuous, whatever the cross module is. Now, in order to discuss the string group, we sort of sense already that finite dimensional algebras will not work out because the string group is already infinite dimensional. So we have to use some kind of infinite dimensional algebras. So which kind? I mean, there is a whole variety of what one can do. And for example, in this work of Stolz-Teichner, they use already von Neumann algebras. So that's a valid choice. So we are sort of saying that if we want to look at the category of two Hilbert spaces, right, sort of natural to have representations in Hilbert spaces, then we take von Neumann algebras, bimodules, and so on over von Neumann algebras. So recall that the composition in this bi-category works via confusion of bimodules. Okay, and then there is, if A is a von Neumann algebra, there is like a unitary version of this thing, where we take not the units, but the unitary elements and star automorphisms. And then what we are going to do is set up a representation of the string group, string 2 group, a unitary representation continuous for a von Neumann algebra A. And the last part of the talk will be to explain what this von Neumann algebra is and how the representation is defined. Yes?
So U of A is actually a binary group?
It's just a topological group. It's right. Yes, I forgot to say this, exactly. So because I will explain later. So the automorphism group of a von Neumann algebra doesn't have a smooth structure. Yes.
Sorry, I missed the motivation for the von Neumann algebra.
Yeah.
Just because this is the simplest non-trivial example.
No, I will come to the. Just give me a second. I'll explain it. Okay, so. So how does it work that we get this representation? I mean, there are all unrelated things right now. And the common thing the point will be that the string group was with respect to a chosen model for this basic central extension. And now we choose an operator theoretic model for this basic central extension that on the other hand gives us this von Neumann algebra. And because that way the two things are related, we can define this representation. Okay. All right, so that's the point. And so everything is based on the Hilbert space of spinors on the circle, d-dimensional. So d is the dimension of the manifold we want to work with, or the dimension of the string group here. So we choose this Hilbert space. So this is a real Hilbert space, has a real structure. And there is all this sort of famous classical things one can now do with this. For example, one can look at the Clifford algebra, which will be a C-star algebra, and there is also a Lagrangian subspace, and that would define a Fock space. And the Clifford algebra has a representation on the Fock space. So we are in this setting, and it's a very classical operator theoretic setting that we are now getting into. So there is this Fock space and this Clifford algebra, and now it's this sort of called the implementability problem that leads to the definition of this restricted orthogonal group of this Hilbert space. You may have seen this before, it's very famous in the book of Presley and Siegel. And this group has a central extension by so-called implementers in the Fock space. So certain elements on this Hilbert in the orthogonal group, certain orthogonal transformations are implemented as operators on the Fock space and act by conjugation. Okay, so this is something that appears in the work of Araki, for example, and Plim and Robinson. And the point is that now we make contact to the other side. We look at this loop group of spin, and it has a map to here. How does it act orthogonally? Well, if we have a loop in spin, then we project to a loop in the orthogonal group just by using the projection from spin to orthogonal group. And then we just act pointwise on the CD by the orthogonal transformation. This will define an orthogonal transformation on all of H.
Still thinking of it as only being not equal to the identity of 0 to pi.
No, here it doesn't matter. This is like all of them.
I should forget about it.
Right? I mean, this is also here the spinors can be supported everywhere, but the restriction will come in a second. Okay. Just wait a second. Okay. So the point is that via this map we can pull back the central extension, and it's a classical theorem that this gives the basic central extension. So we can choose this as a model for our basic central extension, the pullback of this operator algebraic thing. And the point is that these things here, these implementers, this is a subgroup of the unitary operators on the Fock space. So that way, this group comes with a representation already. So this is good for us because we want to construct a representation. All right, so now I have not yet said what the von Neumann algebra is. In fact, it's not this Clifford algebra. I mean, we could complete the Clifford algebra in B of f to a von Neumann algebra, but then it would be a type 1 factor, and that is sort of not helpful for what we're doing for several reasons. So the point is that we have to make it smaller, and we make it smaller by, again, looking at the subspace of spinors only supported on the first part, and then looking at the Clifford algebra of this thing. And completing this to a von Neumann algebra. So it looks like really, really silly, but the type of von Neumann algebra changes drastically under this restriction. It becomes one of these type 3 factors. So this sits in B of f. We complete, so it takes a double commutant, and that's our definition of A. So this is a hyperfinite type 3 factor. It's exactly what, for example, Stolz and Teichner sort of anticipated miraculously like 20 years ago. And here it's exactly the thing that becomes important. So how do we get this representation? So recall that we restricted our string group. So now I would like to move this, but can't. So the string 2 group had this restriction here built in. Okay. And the main point, which we prove, it's a theorem, it's a difficult theorem, is that so that here, the unitary group of the von Neumann algebra also acts by unitaries on F, and this map factors through here in a unique way. So this is a factorization of this thing into this subgroup, and that's exactly what we need for a representation sort of on the morphism level, right? So if I want to write down this on the morphism level, this is here, and U of A had this unitary group of A here, this classical unitary group here. So this is, so R1, the morphism part of the representation, and then we have this map T, PEG, and here we have also a map T from the cross module to the star automorphisms of A. And here is another map, namely the so-called action by Bogoliubov automorphism. So take a path, then one sort of doubles it again to a loop, and then, because then I have an orthogonal transformation, also acts by the universal property of the Clifford algebra on the Clifford algebra, and then extends to the von Neumann algebra. So here's like Bogoliubov automorphism. Okay, and this is the picture of the string representation. Here's the string group, and from both groups we have maps to the cross module of the unitary automorphism group of the von Neumann algebra. And now there are some proofs and theorems involved that in this work with Matthias and Peter we proved, for example, that this factorization exists. So this map lands in this unitary subgroup here. And this is exactly the point where we need the von Neumann algebra. Because if I try to put the Clifford algebra here or something, then they're all too small, or the unitaries in this would be too small. So only the completion to the von Neumann algebra. So here we use some things of the theory of von Neumann algebras that Roberto also talked about. That we can, for example, one can look via Tomita-Takesaki theory on this. Also, one can look at the Haag duality of factors and so on. So there are sort of arguments that are like inherently von Neumann algebraic, and they provide this map into this unitary group. So here it's really necessary to do this completion to von Neumann algebras. And we also deal with the continuity questions. So this unitary group of the von Neumann algebra, it's a topological group. And we show that, I mean, it's a topological group where the automorphism group is equipped with a certain topology, the so-called Hagerup-U topology, and then we prove that this map here, for example, is continuous with respect to this. So we get a continuous representation. All right. And once this is all done, we can go back to this string manifold picture and now look what the Stringor bundle is, the two-vector bundle. Now the idea is we take this string structure and associate, and it's in fact very simple. So it looks like this. So we have this bundle P, which is a principal bundle for this group, and this group now has a representation by unitaries on A. So we can associate via this action just A, and then one can see that this anchor map that I just erased turn this into a bundle of bimodules for the trivial A algebra bundle that we put here. And then there is here a condition involving the confusion of these bimodules over threefold intersections. So that's how we think about a two-vector bundle. So a two-vector bundle looks like a bundle gerbe. It has a resolution by something. Over that, it has a bundle of algebras. On the double intersections, it has a bundle of bimodules. And here is like an intertwiner between tensor products of these bimodule bundles. That's how we think a two-vector bundle should be defined. And this associated bundle construction sort of fits nicely into this. So then one can sort of, once this is obtained, we can sort of look at other things. For example, what is this here? It's like the fiber product of paths starting at X, but with same endpoint. So this is more or less like the based loop space in M at X. So this Stringor bundle in particular has a vector bundle over the base loop space of X. And that's exactly what Stolz and Teichner wrote down in 2006, like a bundle of Fock spaces over the loop space. And this theory sort of puts this into the picture of two vector bundles. So we exhibit this bundle as a bundle of bimodules for an algebra bundle, satisfying a compatibility condition here over triples of paths. All right, and sort of that's it, just one comment. So where can one use this? So right now it's all very new, and now we could sort of go on and study it. So for example, we want to study connections on these two vector bundles. That's certainly the next thing to look at, and then try to, for example, try to build a field theory from this in the sense of smooth functorial field theories Stolz-Teichner way. So the idea would be that this two vector bundle, the Stringor bundle, is the value of such a field theory on the point, right? The value on the point has to be a two vector space, but these functorial field theories are fibered over manifolds. So on the point, one needs a two vector bundle. And we believe that it's exactly this Stringor bundle that creates as a value on the point the supersymmetric sigma model as a fully extended smooth functorial field theory. And this sort of confusion product that I didn't talk about, but that is here, that's responsible for the composition of lines in this field theory. So, right, if it's extended, then it has not only circles, it also has lines with endpoints, and they can be composed, and then one needs exactly this fusion product. All right, thank you very much. Yes, at least sort of some version of string theory. Yes, so if right, so it's not exactly. It's maybe called the heterotic string, where you have this combined bosonic and fermionic field, and where it's possible to carry out this path integral over just the fermionic part, the fermionic path integral, right? And this path integral has this anomaly. It's sort of, when one writes it down, it's this Berezin integral over a supervector space, and it's anomalous in the sense that its value, if one does it rigorously, is not a function, but just a section in a line bundle. This line bundle lives over the mapping space of a surface, and if the manifold is a string manifold and is equipped with a string structure, then this Pfaffian line bundle has a trivialization, and this anomaly goes away. Yeah, that's in fact a theory. That's a theorem of Ulrich Bunke from 2010. He proved this. If you have a string, you need a geometric string structure actually, so one equipped with a connection, and then this anomaly is cancelled, and the fermionic path integral of the superstring is rigorously well-defined thing.
Why did you mention quadratic specifically?
Maybe it was wrong. I was like thinking about this formalism where you have a sigma model and you have like a bosonic field with values in the target manifold, and then sort of accompanying you have a spinor field, like any string theory. Fine. Okay. Sorry.
Quadratic is a candidate because it has abundant
Okay. Maybe yes, yeah. But to be, okay. Okay, thanks.
So this is a very vague question, but so there is a circle. The circle group acts literally on base groups and on paths.
Yes, by rotation.
By rotation.
Yes.
And then, translation.
Yes.
And I think T is equivariant, but obviously we can't make the cross module S1 equivariant, but maybe weakly S1 equivariant. So that's kind of my question. Is there a weak action of S1 on everything you did?
Yeah, that's a good question. So this goes a little bit into this direction of positive energy representations, where one tries to have this additional S1 incorporated into the picture. Yes, well, concretely to this cross module, I don't know exactly, but we definitely sort of are looking at this Fock bundle over the loop space and wondering if this is rotation equivariant, for example. In particular, in the context of what I mentioned at the beginning, of the context where we want to go to this TMF, right? TMF has this sort of partial realization by Tate K-theory, which is formed by vector bundles on the loop space that are equivariant with respect to the rotation. So that's our plan, how we want to associate Tate K-theory classes to two vector bundles by looking at this S1 rotation action here, yeah. So I think that this Fock bundle, this will be equivariant. It's difficult. Maybe only under the central extension by the diffeomorphism group of the circle, by the Virasoro group.
That restricts the circle as a trivial circle.
Yeah, but to another circle. Sorry. Maybe I have to think about it. Sorry. I have what?
You have a Chern-Weil theory.
Oh, a Chern-Weil theory. Yeah, I think that Urs Schreiber has a complete Chern-Weil theory for this, yes. Right. Yeah, I'm not really sure about this. Oops. Maybe I can just drop it. I'm not completely sure if this, in how far it is developed, and I don't know much about it, sorry. I just know, for example, if you have abelian bundle gerbs, like where this cross module is just the example one, that it is sort of possible to calculate the characteristic classes of gerbs in real cohomology by putting a connection, then taking its curvature, and then take its de Rham class, so like as you do in Schoenwald theory. So there are sort of aspects of it working, yes. A complete Schoenwald theory, I don't know. But I think that people have looked at it, yes.
So I have a vague question. So string theory mathematically is a market subject. The best I can think of, I don't know, Schiffel vertex algebras or Schiffel supersymmetric vertex algebras. Is this structure here?
No. No. This seems to be a matter of quantization, but we're not quantizing here. This is just the classical superstring. With this, what I just said about the anomaly is sort of to do this partial fermionic quantization. And
But the question, what do you mean by this word that I'm asking? I have no clue.
well, in this setting where that's a setting I know, right? Where you have like, you can write out the fermionic part of the action functional and just integrate the fermionic fields out of it.
For mathematician, does it make sense?
No, that makes sense. That can be rigorously well-defined using the theory of the Berezin integral. And so there is theory of that, yeah. And one can even, I mean, this is a theory of Pfaffian line bundles that you get. That's sort of classical index theory. And when the manifold is a string manifold, then this Pfaffian line bundle that you have then becomes trivialized. So that then this section in this Pfaffian bundle becomes a function, and that's the integrand of the fermionic, no, of the bosonic path integral. But we are not go any further of this. I mean, the bigger picture is that we want to go into this direction of the Stolz-Teichner program, which is saying we have to identify types of field theories with cohomology theories, and then quantization will correspond to some cohomological operation like the push forward. So that would be the idea how to go. Vertex operator algebras, sorry, I don't really see here.
Maybe a speculative, naive question, but would you then expect that these other terms that are missing on the highest blackboard, the higher terms, would be related to some, I don't know, higher notion of cross modules? I mean,
yeah, they are, yes. I mean, there is theory for this. I mean, of course, you have to, at some point, I mean, after the string group, you have to go to infinity, because the next step is the so-called five-brain group, which has looked at by M-theory people, and that's I think it's a 6 group. So it doesn't make sense to look at 6 categories, so you have to understand this in the infinity categorical world, and Urs Schreiber has a lot of work on this, so people...
It makes sense to look at 6 groups. It may not make sense to look at 6 categories.
Yeah, okay. Yes, that's what I meant, sorry. Yes, that's what I meant. You can look at...
I mean, 6 groups are fine.
Yes, sure, sorry, yeah. 6 groups are fine, as defined in the world of infinity categories, or infinity stacks, or whatever, but not... Yeah, Kahn complexes, fine, that's fine, yes.
And if you want to, I mean, what you were doing was in some sense looking at minimal Kahn.
If you want, yes, yeah. Because it works, so we are not we don't have to go any further, and as long as we don't have to, we are not doing it.
So I have a question related to that. Is there another model, perhaps weaker, but that it would be finite dimensional for this?
Yes, Chris Schommer-Priest has proved that such model exists, yes. But it's difficult to provide the data, so it's sort of related to this construction of the basic bundle gerb over a simply connected group, which has constructions by Gawecki, for example, and Meinrenken, and that's fine, but then you need to make it multiplicative. And that's difficult. I mean, this is simply, I think, not carried out because it's really complicated. And that would be sort of necessary to provide the data you need, the finite dimensional data. And you see, that's important. I mean, the difference between existence and having a model is important for the construction of this representation, because we can only construct a representation when we know what the data is, right? And here we choose this representation theoretic model for the basic central extension and then go on. So in this finite dimensional model, I don't know how to do the representation theory there. But it's definitely, a task to do it, yeah.
Okay. So.
Thank you for all the questions.
Thank you for your